start the next module, module 5, which is on field effect transistors. Field effect transistor, after BJT, bipolar transistor, it is the second generation transistor. BJTs, the bipolar transistors, were developed first, and FETs, as popularly they are called, they came later. FETs are very widely used, particularly in integrated circuits. Today, if we look for the total volume of electronic circuits, then I mean rough estimate is that more than 75% circuits, they are of FETs. FETs are very different as compared to the bipolar transistor. Some differences I can specify right now, that field effect transistor, it is a majority device, majority carrier device, majority carrier device. And you know that bipolar transistor, the main function on which the total operation of the transistor depends, that is when the carriers are injected from the emitter to the base. Now, in the base, the charges which are injected from the emitter, they are in minority. For example, if we talk of NPN transistor, then emitter is N type and base is P type. So, in the P type base, electrons are injected from the carrier. So, electrons are in minority in the base region, and that is the reason that bipolar transistor is called a minority device, minority carrier device, and in contrast FET is a majority carrier device. This is one difference. Then the whole operation, I do not want to go in details, we have finished that earlier, that BJT is a bipolar device. BJT is bipolar. That means for the operation of a bipolar transistor, the transistor, we need holes and electrons both. For example, in the base region, the recombination of charges takes place, which gives rise to the base current, which is very essential for the operation of the transistor. So, that is the reason that it is called bipolar device. We will see that FET, field effect transistor, FET, which is field effect transistor, this is unipolar. Unipolar meaning either we need electrons or holes, not both in the same device. So, this is a unipolar device. In the BJT, we always talked about currents, the emitter current, the base current, the collector current, and the currents flow within the device because of, largely because of diffusion. Diffusion, as you know, that diffusion of charges occurs because there exists a concentration gradient, and that gives rise to diffusion. Obviously, diffusion is a slower process. We will see in this field effect transistor, this is the drift of charges. The operation depends not on diffusion, but drift of charges under applied field. So, it is a drift device. FET is drift device, drift current device. And we will see here in the BJT everything is controlled by the current, and every time even in the analysis we saw that we have to calculate the currents. Here the voltage, particularly as we go through the device, the voltage at the gate will control the current flowing in the circuit. So, it is a field effect, field device. It is not current device, it is a field device. FETs are field devices or voltage operative. In contrast to the BJT, which is current operative. Now, what are the reasons? Let us talk of some features that makes FETs very popular today. These are, I can give a headline, reasons for the popularity, and by popularity here I mean vast use. Of FETs. One reason is that the operation, as we will see, the operation is very simple. Operation of FET is very simple. When I say it is simple, that means we are comparing it with BJT. As compared to BJT, the operation of FETs is much simpler. Second reason is design, the fabrication. Fabrication is much simpler. It can be fabricated in fewer steps, that is FET can be fabricated in fewer steps. And the next point, which is all these points are very important from integrated technology point of view, but this next point is very significant, that a FET device takes 1/5 or lesser area for one device on the chip. I repeat, the area required for a single FET on the chip is at least 1/5 of BJT. As a result, very high density of devices on the chip. High density of devices, very large number of, because the area which a MOSFET device, this FET device takes is very small, at least 1/5, and hence the density is very large. You will be surprised that now in 1 square by 1 square chip there can be a million transistors, that means FETs, and another kind of FET which we will study, MOSFETs, and they can be fabricated all properly connected. Very surprising, our imaginations fail to imagine the size when on a chip a million FETs are there, what will be the size of each FET, and all working well connected. The next point is, which is also very significant, that FETs, field effect transistors, can be used besides as a amplifying device, besides as a amplifying device. FETs can be connected as passive components like resistors and capacitors. Resistors and capacitors. So often the circuits will contain only FETs, where some FETs will be simply they will be functioning in the circuit as resistors, while others will be as active devices and some as capacitors. Broadly speaking, FETs are of two types. One is the junction field effect transistor. Junction field effect transistor, which is abbreviated as JFET, junction field effect transistor, JFET, or simply FET, or simply FET. When we say FET, normally we mean junction field effect transistor. Now, then we have the another kind, which is metal oxide semiconductor field effect transistor. Metal oxide semiconductor field effect transistor. Field effect transistor, that is written as normally, and in fact always we write it as MOSFET. MOSFET, metal oxide semiconductor field effect transistor, MOSFET. These two types are very widely used, and in integrated circuits mostly, as we will see, these will be the MOSFETs. First, we will study the junction field effect transistor. Having introduced, I am sure you have followed the basic differences as compared to BJT and the reasons for popularity, why FETs are so widely used in circuits. Now, we go for junction field effect transistor. Junction field effect transistor. The construction is like this. Here, let me at the beginning remind you that since we are talking of a different device, now the terminology used will be quite different, and it is better that you should get familiarity with the terminology used in FETs. So, here this is a substrate, a n type substrate. This is n substrate, normally n silicon. About dimensions we will talk later. Let us just take it is a chip of n silicon on which two regions of heavily doped p type, this is p plus and this is also p plus, they are developed, they are fabricated, they are grown. Heavily doped p regions on the two sides of a small crystal of n type silicon, and one electrode is deposited here, the other electrode is deposited here, and then there are these two electrodes, these are all like aluminium, and these both are internally shorted. The two p type regions which have been formed on the two sides of a small crystal of n type silicon, they are shorted internally. And now what these are called? This is called source, this electrode is called source, this is called drain, and this one is called gate. There we have emitter, base and collector. In FETs and of course for in the MOSFETs the same terminology, we have source, gate and drain. Just for the sake of comparison only, that source is almost like the emitter, gate is like base and drain is like collector. Now, this is called the channel, in between the two gates is called channel. This is n type channel, n channel. What will happen when this is n type silicon, n substrate over which we have grown two p heavily doped p regions? For the reasons which we have discussed in the p-n junction, wherever n and p type semiconductors meet, that means if there is a structural continuity, then the natural processes which will start from diffusion and followed by drift, that means a depletion region will be formed. I repeat, this is the substrate n type and this is p type region, this is p type region and this is heavily doped. So, a p-n junction kind of thing will occur of course, but more important than that is a depletion region will be deposited here. Here this is a depletion region and here also there will be a depletion region. I draw a more neat and clean, a bigger size figure, and then I explain what will happen when we apply voltages. This is the device in equilibrium here. This is source, this is gate, drain, these are the p type regions. This is p plus, this is p plus, and here is the depletion. This is depletion. Similarly, a depletion region will be formed here. This is depletion, and here we put a electrode, here we put another electrode. These two are internally shorted, that means they are connected together. When we apply a voltage, the voltage will apply simultaneously on both the gates, and this is gate. This is, I think, very clear. Now, this is the p type region and this is the depletion region, and here this is n type, n silicon substrate, and this is the channel, this is channel, this is channel, channel. This is about the construction of a junction field effect transistor. Now, to understand its operation, I will first consider the case that gate is kept at a ground potential. It is at a 0 potential, it is grounded. In fact, source is also grounded, and between source and drain we apply a voltage keeping drain side as positive. Let us see what will happen. This is a battery VDD. This is the source which is written as S, this is drain, and this is gate. Gate is at 0 potential, at ground potential, it is grounded, and we have applied the a positive voltage to drain with respect to source. Now, what will happen? This is the channel. When we apply a voltage between the two ends of a semiconductor, then charge carriers will flow and a current will start flowing. Here, because this channel is n type, n channel, and this is the positive electrode drain. So, electrons will flow into this, they will come out and they will enter from here, and drain current flows in this direction. Here in this direction, the drain current written as ID. ID is the drain current which will flow. So, as we start this, let us keep this varying. As we start this source drain voltage from 0, then as soon as we move further, the current will start flowing, and larger the voltage, larger will be the current. Now, what happens to the depletion region? That is very interesting, and I will show that this current will start rising but will not continue to rise indefinitely. There is another effect which comes into play, and that will stop that rise, and after a certain value the current gets constant. What happens? The depletion region, this was the depletion region. Depletion region will be widened in two ways. You remember we said that depletion width of a p-n junction increases on reverse bias. Remember that in the p-n junction, if this is p type, this is n type, and this is the depletion region, if we increase the reverse bias, that means p region is given a negative potential and n given a positive potential, then this is widened. This is the new depletion width. Now, here depletion width can be changed in two ways. Both way, of course, we are reverse biasing the p-n junction. So, there is a widening of the depletion region, and both are, there are two gates. So, widening will be from both sides. Now, what are the two ways? One is, if we give, this is p type gate, if we give a negative potential to the p type gate, then depletion region will increase, it will be widened, number one way. And another way is, you see that here this is a semiconductor having a finite resistance, and that resistance is dropped all over. Between these 2 points resistance is different, these 2 points it is different, and so on. Accordingly, the field is spread all over. It is maximum positive here and least positive here, like here. For example, if I take a simpler, to make my point very clear, this is very essential what I am going to say, that how the shape of the depletion region changes. It is oblique, it is different shape, and what happens that, for example, suppose there is a resistance wire and these are 10 loops, and we apply here a voltage of 10 volts. If we measure, now these are roughly, I have not done all the 10, but let us see, these are 10 in number, 1, 2 and 10. If we measure the voltage between these 2 points, it will be 10 volts. If we measure between this point and this point, it will be 1 volt, 2 volts, 3 volts, between this and this, it will be 3 volts, between this and this 4 volts, and so on, it will go on increasing. In the same way, here the voltage, when we have applied VDD, which will be largest here and least here, between this point and the very close to this surface, the potential will be almost 0. Between source and middle, it will be roughly half of the voltage which we have applied. If we have applied 10 volts, between center and here, it will be 5 volts. Between the source and this end, it will be 10 volts. Now, we can reverse bias the junction either by giving a negative potential to the p type material, or very important, a positive potential to the n type region. I repeat, we can reverse bias the p-n junction by providing, suppose one is grounded, then we provide a p type negative, more negative, more negative with respect to that grounded terminal, maybe n type, then broadening of the depletion region will occur. and or if we keep this at 0 potential by grounding the gate, if we increase this potential which is increasing this way, decreasing this way. So, in this region, in the drain, now very important, in the drain region the depletion width will be larger than in this region, for the simple logic that in this region closer to the drain the PN junction is more reverse biased as compared to this region. Now, another important fact that I said these two regions, they are heavily doped P regions. I am sure you will recall it was said that if one region out of these two P and N regions, this is P region, this is N region, if P region is heavily doped, then the broadening will occur and the broadening will be spread much more in the less doped region. And so, this channel region is less doped, hence the most of the broadening will occur into the channel region. If you have followed what I have said, then there is no difficulty in understanding that earlier this was depletion region was symmetric. Once we apply a voltage between source and drain, keeping the gate at 0 potential, then increasing this voltage will give you this shape. This shape of the depletion region. This is the depletion region. Now, when we keep on increasing this voltage, these 2 points, the depletion regions will come closer and closer, and the shape will be maintained, and obviously a situation will come where at one point the two will meet. That voltage will be called pinch off, and it is written as Vp, pinch off voltage. What is pinch off voltage? That minimum voltage between drain and source at which will make the two depletion regions, the lower gate electrode and the upper gate electrode regions, touch at one point. That will be called pinch off. And now this is not difficult to follow, that because of this spread of the depletion region, the channel conductance, the conductivity of the channel is changing, it is falling. Depletion region, I am sure you have not forgotten that depletion region is a high resistivity region, and so the channel width falls, channel width is falling and the resistance will increase. So, the current levels off, it becomes constant. Now, what I have said, if I plot the drain current as a function of drain source voltage, that is this plot. This is drain source voltage in volts and this is drain current. This is 0 volts and this is 5, 10, 15, and here this may be 20 milliamperes, 40 milliamperes and so on, 20 milliamperes, this is in milliamperes, 20, 40, 60 and so on, depends on the device. This can be 100, 200, 300 milliamperes and the voltages can be 30, 60 and so on. So, now from 0, I said this voltage we are changing from 0. So, the drain current will increase and it will keep on increasing. With this increase, what is happening, that this depletion region is spreading more and more towards the channel, and the moment the channel the two channels I mean the two depletion regions touch each other, pinch off occurs, and by then the extent of conductance that nullifies the effect of the rising voltage. So, at that the current is levelled off, it does not increase further, and this voltage, this is Vp, the magnitude of the pinch off voltage, but here the pinch off has occurred. Now, you may ask that once the pinch off has occurred, why the current is constant? By further increasing this voltage, why the current is not increasing? Very valid question, and let us try to understand this again. Once at this point the pinch off has occurred, that means this is the channel through which charge carriers are flowing to form the current. Now, this is the depletion region, and at the pinch off here, at only at very small region at one point, the two depletion regions are contacting. As we increase this voltage, then this contact region increases. That means, at this voltage the channel is like this. It is here, it was touching at one point, and here it is touching all through in this region, and hence it stops the rise of current. The effect of increased voltage to increase the current is levelled off by this rise in the resistance of the channel. The conductance falls, as up to here it gradually the current is increasing, the channel is not pinched off, but here pinch off starts at one point only, and then when we further increase, then the more and more region lengthwise the channel comes in touch, it is touching with one another. The two depletion regions touch along the line, and this width of the line of touch increases with this voltage VDS. So, this is this. Now, if we further increase VDS, then suddenly there will be a rise in the drain current. This is because of the junction breakdown. This is junction breakdown. We talked about the processes in the case of a PN junction, that junction breakdown occurs when the reverse bias voltage increases beyond a certain point. You remember that IV characteristics of a PN diode, this is I, this is V, this is the very small current, and suddenly the current increases. This is the breakdown region. Same thing happens here, and this is called, this voltage is called VDX max. Max means maximum. We are not supposed even to operate in this limit. the voltage has to be less than VDS maximum value, which is prescribed by the manufacturer on the in the data sheet. Now, this current, maximum current, this is known as IDSS. When this is the maximum current in a JFET. Let us, this was, if I am sure you have followed these characteristics, and this is when VGS, that means gate source voltage is 0, because we grounded the gate. What we have drawn, these are known as drain characteristics of a field effect transistor, drain characteristics. We get plots when we change the gate voltage from 0 to more and more negative. That means the total, the what we call the drain characteristics. Drain characteristics can be obtained, and these are we will not anyway, it is all right. This is this. This is drain current in milliampere, this is VDS, and this is IDSS, the maximum current, and this is at VGS equal to 0, this is minus 1 volt, minus 2 volt, minus 3 volt, and so on, and then finally this will be at minus 4 volts for a, I have taken numerical values, this may be true for a particular JFET. For all JFETs we will get a similar plot, only difference may be that these currents may be different, these voltages may be different, and this is the pinch off voltage. These are the complete drain characteristics for. Now, why when we make the gate more negative, why the current falls? If the discussion which we have made earlier, if you have followed that, keeping this drain source voltage fixed, if we change the gate voltage, make it more negative. Making gate more negative means what? We are reverse biasing this P region and this P region. Depletion will increase, and it will increase towards the channel. So, instead of 0 volts, when we make it minus 1 volt, then the keeping this constant, the conductance of the channel will fall, because in the channel now more portion of the depletion region exists, and hence on increasing the gate voltage, the drain current will keep on falling, it falls, it decreases, and a situation comes when the drain current will be 0. and this is known as VGS off, which makes that gate source voltage, which makes drain current equal to 0. And obviously, we will see this that VGS off is equal to magnitude wise is equal to the magnitude of Vp. Now, the device which we have been talking so far, this is the channel was N type. We started with the N silicon and the channel was N type, and this is actually a N type junction field effect transistor, NJFET. We can have a P type junction field effect transistor as well. For that, we will have to start with a P substrate, P silicon, and N type regions. These are the N type, heavily doped N type gate regions. We will apply the electrodes, and these two gates, they will be internally shorted to each other, so that externally only one lead is available, and this is gate, this is source, and this is drain, and same thing, depletion regions will be here. This is now P and this is N region, this is N region, heavily doped N regions. Here same thing, except now when we apply a positive voltage at the drain with respect to source, then holes will take part in the current process. So, holes will give rise to drain current. This is positive, this is negative, holes will flow in this direction, and so the direction of the movement of holes is the direction of current. So, this is the drain current. Here, to reverse bias, this is N type, mind it, to reverse bias the junction, the gate has to be positive. So, the characteristics will be the identical, only the polarities will be different. Here we have taken VGS 0, VGS 0, here also will be the same, but here these voltages have to be positive. So, the drain characteristics will be exactly the same. This is IDSS, this is VP, this is VDS, and this is ID, and this is VGS, gate source voltage 0. Now, here this is difference, plus 1 volt, plus 2 volt, and so on. So, everything is same, but obviously the mobility of electrons is higher. So, N type JFET is more popular as compared to the P type JFET. JFETs, junction field effect transistors, are fabricated in discrete devices as discrete devices, and also on the chip in the integrated form. Also on the chip as ICs, they are available. Now about the circuit symbols. The circuit symbol for FETs, JFETs, circuit symbols. This arrow gives a distinction. This is the circuit symbol for a FET, this is gate, this is drain, and this is source. This arrow, this gives, as in the case of NPN transistor, the arrow gives the direction of the conventional current. So, on that it has been derived. This is for N type JFET, and for P type, except the arrow direction is reverse. So, this is gate, sorry, I am sorry, the direction has to be reverse. This is gate, this is drain, and this is source. So, this is the circuit symbol for P JFET. We started with pointing the major differences of BJT as compared to FET, of FET as compared to BJT. Then we talked about why FETs are so popular, that a much larger share in electronics is of the field effect transistors as compared to BJTs. There is one thing which is higher for BJT. The amplification factor is higher for BJTs as compared to FETs. So, BJT are still very much in the picture in the circuits, but there are several other features which make these FETs much more popular. We will continue, we will draw the IV characteristics and then explain everything which we studied about BJT, same. Now it is a different transistor, and we will have to do the same way. So, we will go for IV characteristics, then we will talk MOSFET, and then we will develop other things. The model, amplifying factor we will determine, and what are the parameters which are significant in FET, that we will see.